Okay, so I'm here to talk to you about firmware update, specifically using Internet of Things devices, using the Internet Engineering Task Force's suit working group's current documents there, which are in progress. I think we've talked about security in devices quite a lot today and how vulnerabilities are everywhere. Well, that's pretty obvious to everyone here, I think. And all software does have bugs. That's just to be expected. When you have bugs that have substantial customer impact, well, they require a response. When they introduce security vulnerabilities, the picture historically has been a lot less clear. In air-gapped or non-IoT networks, it's been a little bit less critical because there's a limited impact. Physical security adds some defense in depth. If you can't connect to a device, you can't exploit its weaknesses. In IoT networks, on the other hand, devices are accessible. That's the whole point. So they naturally have a broad exposure, and that makes vulnerabilities high impact, and they require a response. So what can we do to respond to vulnerabilities in IoT devices? We've seen all of these responses over the years. Ignore them and hope for the best. I think that's one of the more common ones that have caused the exciting headlines we've seen. On-site service, there have been a few headlines about devices that had to be reprogrammed in the field with JTAG cables. We can recall them and refurbish them, where you send a device back to its manufacturer, and if sometime later you can reinstall it. Or more commonly, I think now, decommission them and replace them. These are each expensive, either in reputation, money, or both. So what about another option? We fix the bugs remotely. Well, IoT devices have network connectivity, so we can use that to patch them. And many jurisdictions, as we've talked about, are actually considering making patching capability a requirement. In fact, the NCSC's Code of Practice lists that as its third most important item. Patching is also the single most important security repair tool that we have today. If your security is broken, patching is the only way to solve the problem. And remote patching makes it viable to fix vulnerabilities in IoT devices. Now, it's simple. You just download a new firmware and install it, right? Well, there are some risks. There could be a power interruption, a network interruption, a firmware mismatch where you send the right firmware to the wrong device, a network mismatch where you take a perfectly valid firmware for the right device and give it a firmware for a different kind of network. Stability. Maybe the new firmware isn't quite as robust as the previous one and your devices keep crashing. There could even be processing errors where you apply, for example, a differential update to a device that doesn't have the precursor firmware you expect on it. From a security side, there are also some update risks. I mean, the whole point of patching a device is to explicitly allow remote code execution. And that's something we normally try to stop. So that requires some additional consideration as well. There are other ways that unauthorized updates could happen as well. Rollback's particularly interesting, where you take a totally valid firmware from a valid party for the right device, and it's just a bit older than the current state of the art and has some vulnerabilities that everyone knows about. When you're sending your firmware over a network, you risk IP disclosure, where people are able to extract your sensitive algorithms and use them. Now, other sectors have solved a lot of these problems. In PCs, automatic updates are the norm. In handsets, they're the norm. And in fact, everything we do in security is based on the ability to update software. If you can't update software, there's no point in doing vulnerability disclosure. If you can't update software, there's no point in developing patches. So why do we struggle so much with automatic updates in IoT? Well, there are some different challenges in IoT. On PCs, automatic updates are typically done by each application. You can see this in web browsers and a variety of other applications. Some of them use platform services now, but it's on the uptake. It's not the most common approach. In handsets, the OS updates are provided by the handset vendor, and the app updates are provided by the platform vendor. So again, these are sort of single device systems. homogeneous device systems. So why is it not the norm in IoT? Well, there's commercial complexity to start with. There may be insufficient incentives. It's unlikely that a vendor will receive money for issuing an update. There may be not enough reputation damage to be a concern if updates aren't deployed in a timely fashion. And there may not be enough regulatory or legal incentives to push a vendor to deploy updates, though that is changing. It's high risk. We talked about a number of the risks. So when you combine low incentives and high risks, it's not attractive to deploy an update. And user intervention is frequently unavailable, which makes things even more complicated. There's also technical complexity to add in. You have a heterogeneous mix of devices. Rather than the single device systems, pushing browser updates to a browser is fairly straightforward, but pushing an update to a large number of dissimilar devices is quite difficult. Devices are also constrained in a number of ways. Bandwidth, energy, storage, processing power, each of these limits what you can do in an update. Bandwidth limitations mean that compression is needed, but at the same time, processing power limitations limit what kind of compression you can use. Energy decides what kind of cryptographic algorithms you have available to you to protect your updates. And storage limits how many updates you can have and what your fallback options are if an update should fail. And frequently, there's no platform to provide update machinery for IoT devices. In homegrown systems, you may not have the ability to get your update system provided to you. Now, this should be a solved problem. We've had connected devices for many years. Fleet management systems have been around for ages, and there are sensor networks that have been deployed widely. And there are a variety of IoT platform vendors that already are out there. So surely we should have a mechanism to handle deploying updates to large networks of dissimilar devices. Well, there are a few. We could have seen just plain signed binaries, where you have a firmware with a signature attached to it, and that's all. We've seen binaries with secure boot metadata. That's fairly common, in fact. That's just the firmware, some boot time metadata, and a signature. And that at least gives us rollback protection, typically. There is a very robust standard out there, PKCS number 7 for firmware. And it just hasn't had a lot of uptake. It's very rich metadata in a PKCS 7 container. And then there's the update framework, which has a very extensive metadata, and it has many signatures involved in it. And there's an implementation of that called Uptane, which is targeted at automotive sectors. Now, for adoption, there's not a lot of information available. Major IoT platforms typically offer firmware update solutions. The firmware update solutions that they offer tend to vary based on the platform vendor. Many platform vendors have their own proprietary implementations, and they typically do fall back on the secure boot metadata when they don't have their own proprietary implementation. So the status quo that we have today is a fractured market. I've seen lots of approaches to firmware update, ranging from no one else should deploy firmware to our devices, so we don't need a standard, to the server creates all the metadata so that each device can have an update tailored to it. We've seen situations where a single vendor system is the only one that can receive updates, and any devices in it that aren't from that vendor don't get updated. We've seen manual intervention required because OTA updates are too hard. And we've seen people say that a homegrown system is the only answer because no standard provides for them. So is it a problem to have this status quo? Well, I think so, but it does depend on the business model. If your product, or it might not matter for you, but only if your products do not interoperate with other vendors' products, and you have a direct relationship with the end user, and you have the expertise to deploy and secure an update solution either in-house or from a platform vendor. Now, I think it is a problem for you if your products interoperate with other vendors' products, or there are intermediaries between you and the end user, or you do not have the expertise to deploy and secure an update solution. So we want to change the status quo. And the Internet Engineering Task Force, the IETF, has chartered a working group, which is Software Update for the Internet of Things, or SUIT. SUIT's charter includes providing a standard for updating constrained IoT devices, describing the overall structure and requirements of firmware update systems, including the involved entities, the various actors and operators in a system, the security threats to the update process, any assumptions that are made about the system as a whole, and specifying one or more manifest formats, though it appears that one is what will happen. Now, SUIT is backed by interested parties from across the industry, including ARM and some of ARM's partners. The goal of this is to lower those risks and increase the incentives for deploying updates in a timely manner. Now, we need to set the right standard. We've been trying to do this by having consultation with interested parties to make sure that we're covering the right needs. We've developed a list of involved entities in the firmware update process and a set of exemplary use cases, which should cover the majority of use cases. But we need more input. If we haven't covered your use case, then our standard isn't useful to you. So come talk to us and make sure that we can cover all of your needs. So what will we provide? Well, first off, we'll provide common threat and security models. And this goes back to what one of my other presenters was discussing earlier, that security engineers need to communicate better with the end user developer. And this is our attempt to do that. We want to help developers consider the security challenges in IoT updates. We're also working with ARM's platform security architecture. Now, if you're not familiar with this, it's a set of standards that ARM has produced for describing the baseline security requirements for developing secure devices. We define a very similar and compatible security and threat model for update, and ARM's PSA actually recommends SUIT for firmware updates. And we share a common approach for security of firmware update for IoT. The standard's going to define a common metadata format. Now, that's really important to reducing those risks. It allows reference implementations for testing and validation, and will enable companies to have faster time to market by using libraries, as mentioned by other presenters today. And we'll also get better security through increased scrutiny of those libraries. If more people are looking at it, there's more chances to spot bugs in advance. We'll give consistent tools to intermediaries so that operators in a system have some hope of updating devices in coordination, so that many devices from different vendors can be updated simultaneously, where that could cause breakages. And this will also provide more interoperability between devices and management systems by providing a common format that management systems can understand, and easier coordination of updates to these interoperating systems. So the manifest today is a bundle of software update metadata. It's encoded in CBOR, which is a binary serialization, and it's secured using COSI, which is an encryption wrapper also using CBOR. It's designed specifically to be broadcast and multicast friendly in the way that it's constructed. It targets very small devices, but it's also good for very large devices. It natively handles both single component and multi-component updates, along with dependencies as well. It takes a unique approach to describing updates. It doesn't describe necessarily the data in a conventional document format. Instead, it encodes the data into a compact and simple, but extensible and very flexible update language. The result is quite small and easy to parse, and that's been a focus. The text metadata are also available in this format, but they can be stripped before sending it to a device to limit network traffic. This helps operators to understand exactly what they're sending to devices. So today, we have 3 documents. There's an architecture definition, which is approaching completion and should be standardized before the end of the year. It contains high-level definitions and requirements for IoT firmware updates. There's an information model, which contains our security assumptions, our threats, user stories, and any requirements that are generated from those. It's also approaching completion and should be forwarded on for standardization by the end of the year. The manifest serialization is quite stable now, and it's approaching completion. It should be done in early 2020. And it's a serialization of the information model, and it's specifically designed, as I've said, for low complexity parsing. I'm encouraging you, please get involved in this effort. We need to know about use cases. If you have use cases that you care about, talk to me about them. I'm here later, and we can get involved in the mailing list as well. If you are building IoT devices or services, we'd really love to have your input. If you want to collaborate, please review the drafts. They're available on the SUIT working group page, which is linked there. We're having a hackathon in February, and it's free attendance. I'm afraid I don't have a link for it in the slides, but I'm happy to hand it out. And we have another IETF meeting coming up in March where much of this will get discussed as well. So with that, thank you very much.
Thank you.